So we're going to start off lesson 17 with this graph about consumption of milk and soft drinks in the U.S. In the years after 1950. And it says there's 4 useful ways to represent most mathematical relationships. You have graphs, tables, a verbal description, and then you can have an equation. Each way has advantages and drawbacks, good things and bad things about them. And so we're going to start here with this one with the graph. So if we look at this, we can see that we have 2 different lines that are being used. We have a dotted line that is for the soft drinks, and then we have a solid line that's for the milk. Over here, it tells us that this is in gallons, and it says it's the approximate average U.S. consumption, and over here it says per person. So this is the how much each person on average in the U.S. consumed. So for instance, if we pick right here, this looks like it's a little bit above 35, about 36. So this is milk. This is 0 years after 1950. So this is actually 1950. This is 10 years after 1950, so this is actually 1960, 1970, and so on. So this is 1950 for milk. So in 1950 for milk, the average person in the U.S. consumed 36 gallons of milk a year. Okay, so that's what that means. If we go over to another one we could see, try to find one that's kind of easy to read. So 40 years after 1950, which would be 1990, this is for soft drinks, the average person consumed 40 gallons of soft drinks in a year. Now, we've had discussions in class about what is a soft drink, and it kind of depends on where you look, and it never tells us here how they defined it. And so we could probably go to the, it does reference where this came from in the actual materials, and so we could probably go and look there. But by definition, we have typically found that soft drinks is soda, carbonated drinks. They didn't include things like lemonade or Gatorade or tea and things like that. So in most of the definitions that we found soft drinks to be actual colas and things like Sprite and Dr. Pepper and things like that. Okay, so now it says we're supposed to write down 3 general conclusions we can draw from the graph. Well, the things that are very often noted is that the soft drinks is going up and the milk is going down. Okay, so soft drinks is increasing and the milk is decreasing. And not only that, milk started higher but ended lower. So if you look up here, you'll see the milk started as the higher number, but it ended below the soft drinks. And another one that people often notice is this cross right here. And it just says general conclusion. So you might have seen some different general conclusions and it would have been just fine. But it does look like in 1975 it was the same. So in 1975, the average was same for both at about 30 gallons per year. So in 1975, it appears that on average, people drank in the U.S. about the same amount of milk as soft drinks, and it was about 30 gallons each in a year. So now it says for number 2, we're supposed to get more specific. Estimate at least 4 ordered pairs and be sure to use each graph at least once. Well, I'm going to write down one that I'm just going to kind of say is extra. This is on both of them. So for both of them, so we have for both of them the point 35, which is 35 years after 1950, or 25 years after 1950, or 1975. Fix that. And so both graphs, or both lines, line segments have the point 25, 30. Okay, so let's do one or a couple now that are just for milk. I could spell milk. And just for milk, a couple that would be important. I mean, you could do the first one, the last one. You could do ones where it looks like it crosses, you know, right on someplace that's easy to read. Whatever you'd like. We already talked about this one, so we'll go ahead and write that one down. In year 0, which is 0 years after 1950, it looks like milk was at 36. And then I'll just go ahead and do this one because it looks like it's easy to read. So it also includes the point 45, 25. So 45 years after 1950, there was 25 gallons on average of milk. And then if we do the soft drinks or the soda, it looks like it starts at 0, 12 maybe? Looks a little higher than 11. This would be 15. This is 10, so that'd be, I think that's about 12. And then for another point for soft drinks, maybe something up in here that's easy to read. This one looks like it's easy to read. It's kind of crossing right on there. So 40, 40. And you could do different points on the graph as long as you got, you know, a couple points off of each one. So now it says to write contextual sentences about to the points you estimated. So we already talked about this, that in 1975 they were the same, so we'll look at these points. So you could say, we'll just actually kind of combine these two. So in 1950, milk started at 36 gallons and soft drinks at 12 gallons. So we kind of actually talked about both of those points. And then if we wanted to pick another point, if we talked about milk, we're looking at this point right here. In 1995, because that's 45 years after 1950, milk averaged about 25 gallons per person. Okay, so this is what they mean by contextual. When they talk about contextual, they mean explain what those points mean in the context of what we're looking at. So what do they actually mean for the data? You can't just say it started at or they were crossing at. You need to be specific. Milks, soft drinks, years, amount, and make it in context for what's going on. So now it says we're supposed to calculate the slopes of the two lines. They have some points up here that they gave us, so we could go back and use our points, but we'll go ahead and use their points. So if we're going to calculate slope for those two lines, we can just pick any two lines we want. I'm sorry, not any two lines, but any 2 points that we want. And slope is just a fancy way of saying what's the increase per year. Okay, so don't let that word scare you and think, oh my gosh, that's algebra class. It's not. I mean, it is, but it's not. All we need to know is how much it increased or decreased. So, for instance, milk went down. If we look at these first 2 points here, it went down by 4 gallons, 36 to 32, in 15 years. So we could just say that's the slope, 4/15, or if we wanted to change it to a decimal, we could say 4 divided by 15 and actually write it as about 0.27. Don't forget the negative because that's important to indicate that the milk is going down, not going up. Okay, and then for the soft drinks, they went up from 11 gallons to 22 gallons. And again, you should be able to do this with any 2 points and get the same answer. But here it went from 11 gallons to 22 gallons, so it gained 11 gallons over, again, 0 to 15, so 15 years. So then if we wrote that as a decimal, 11 divided by 15 is about 0.73. Okay, so it says now, and it says now determine the equation for each line. Be sure to define your variables. Now, this sounds like they're making us make a huge leap here, but they're not, because they gave us the y-intercept. Okay, so the y-intercepts are, and they used 11. I thought it looked more like 12, but we'll use their 11. I thought it looked more like 0.12 rather than 0.11. But we're going to go ahead and use their number here and write an equation. So we know for the milk that the amount of milk starts at 36 and then it goes down 0.27 per year. So that's the equation for milk. It's as simple as that. Starts at 36, this is how much it goes down each year. And then for the soft drinks, they start at 11, but they go up 0.73 gallons per year. Now it says during what time period did the U.S. soft drink consumption surpass milk? And we went back, we already saw this in the graph. It was at 1975. So after 1975, soft drinks was higher. So after 1975, soft drink consumption was higher. If the soft drink linear pattern continued to hold, when or did will the consumption reach 50 gallons per person? Well, if we go over here, we see that the soft drinks did reach 50 gallons. In fact, it looks like it's a little bit above 50, but we'll go with this. What year is that? Be careful, because it's easy to say, oh, it's the last number, it's 50. But you notice 50 is this line, this grid mark, and where the 50 is actually another grid mark over, and these are 5s, 40, 45, 50. So this is actually, if I were to mark this in, this is actually 55. So in it's actually not 19, it's 55 years after 1950, so it's actually 2005. So in 2005, 55 years later, soft drink consumption reached approximately 50. Again, it looks like it's actually a little bit higher than 50, but we'll go with it. So it's about 50 gallons per person. And if the milk pattern continued to hold true, when did or will milk consumption reach 20 gallons a person? So again, we got to go back, make sure we're looking at the milk line, and you'll see at this point it's not there. And so what we could do is we could extend this if we wanted to, especially if you had a straight edge, it would be better. You could extend this down and say, oh, it looks like it's at about 60 years later, or 2010. Or I could go up here to this equation and solve too. I want to know when milk is going to be 20, and I could have done this for number 7 also, but I want to know when milk is going to be 20, and since it's not on the graph, I could just solve this. Subtract 36 from both sides. That gives me negative 16 equals negative 0.027y, and I just divide. How, I have to lose 16 gallons. How much is that going to be if I lose 0.27 gallons a year? It's 59.25. So it's almost to 60. It would be just a little bit before this. So y is 59.25. So you could say a little bit past 2009 or not quite to 2010. So I'm going to put almost 2010. Because that'd be 2009 and a quarter. So it takes us to almost 2010 before that reaches 20 gallons. Next, it asks us to decide which representation would be the most appropriate in each of the following. So let's say you want to display exact measurements for 10 data points. Well, that's what a table does. A table gives exact measurements for a certain number of data points. So that would be a table. What if you're writing a magazine article about population and you would like to include a quick reference illustration? Well, a quick reference illustration is your graph. You can look at it quickly, see the patterns real quickly without going into a lot of detail. You're talking to a friend on the phone and describing how 2 different companies calculate phone charges. This is going to be what we call a verbal description. So since you're talking on the phone, they made it so you're talking on the phone, you're going to describe how 2 different companies can calculate that. And then you would like to provide a short way for your friend to calculate his bill. Well, if we had an equation, that would be the quickest way for you to get any point you needed without having to look at a table or a graph. You could just take the equation, plug in the value that you need, and go with it. So the strengths of a graph are that it's visual. That's its biggest strength. Its weaknesses is sometimes it's not exact, and sometimes you can't get all the data on there. So sometimes you can't fit all the data on there. It depends on how you do what kind of data it is and how you do your grids. But the biggest thing here is it's visual, and people are visual. That's why we have the saying, a picture is worth 1,000 words. People can pick up on details of a graph or a picture a lot quicker than if you're just putting the numbers down in a table or describing it. So verbal, I think the biggest strength of verbal is just that it's more conversational. It's more everyday speech, so it's doesn't get bogged down in the math. So I'm just going to put conversational. It's comfortable for almost anyone. The weaknesses are that it's not visual, and also that it might not have enough detail. So it might be hard to describe all the detail if it gets at all complicated. A table, again, is sort of visual. And it has some exact values, but its weakness is it can only have so many points. So you can't say, I'm going to make a table that has, all the different possibilities in a lot of cases, because it would either be too much or it's infinite. So you can only have so many data values on it. That's the biggest drawback to a table. For an equation, it's exact, and you can use for any value. And its biggest weakness is it's not visual. So a lot of times if you really want to help somebody understand something, using a combination of a table and an equation or a graph and a table really can make the difference. So we're going to continue this discussion about linear relationships comparing 2 different situations. So in this case, instead of milk and soda, we have plan 1 of a cell phone company and plan 2 of a cell phone company. These are kind of old style plans. You don't really see these anymore. But plan 1 has a monthly fee of, so it has like an initial fee of $15.99 plus 13 cents per minute. Whereas plan 2, that's plan 1. Plan 2 costs, and you know what, I'm going to actually do these, try to keep these in different colors. So let's do plan 2 in red. So plan 2 costs $39.99 per month, so it's more per month. However, it has unlimited minutes, so you don't have to pay for minutes. So unlimited minutes basically means 0 cents per minute. 0 per minute. It doesn't cost anything. So how many minutes would you have to talk to make plan 2 worth the higher $39.99 fee? Well, we don't know right yet. We'd have to do a little calculations. They just want us to make a quick prediction. And I have students guess anywhere from 20 minutes to 100 minutes to 200 minutes. So we don't know. 20 100, 200. You know, think to yourself what you think that might be without actually calculating it. So now that we have that verbal description, we're going to go down here and create a table of costs depending on how many minutes you use. Well, I'm going to do plan 2 first because plan 2 is a lot easier. If you talk no minutes, you pay $39.99 for that second plan. If you talk 50 minutes, you pay $39.99. Minutes don't matter with the second plan. So no matter what you do, the second plan is going to cost $39.99. So now let's go to the other plan. For the other plan, oh darn it, I just did that in the wrong color. So I'm going to pause this and fix that. Okay, so now we have that magically fixed. So plan 2, no matter what you do, is $39.99. Now the other plan starts at $15.99, but it goes up 13 cents a minute. So $15.99 is going to be for no minutes. Now be careful, we're not just adding 1 minute here, so we're not just adding 13 cents. We're adding 50 minutes. So 50 minutes times 13 cents a minute. If you add 50 minutes, that's going to add $6.50. So every time you add, you go up by 50 all the way down here. They all go up by 50. And you have to make sure that, you know, that pattern over here is going the same before you do something like this. But since every one of these is going up by 50, we're basically each box going to add $6.50. So $15.99 plus $6.50 is $22.49. It's essentially 16 plus 650, but so $24.90. I'm sorry, $22.99. And then we're going to add another $6.50, and that's going to put us at $28.99. Oh, I'm just riddled with errors here. Sorry, this isn't 99, this is 49. So $22.49. All right, and then if we add another $6.50, we're going to reach $35.49. Another $6.50, we're going to reach $41.99. Then $28.49. And then $54.99. So you'll notice when we get to 300 minutes, Plan 1 is definitely more expensive than Plan 2. If you talked 300 minutes, you would not want to get Plan 1. You would want to get Plan 2. So where's the difference at? At what point should we decide to do Plan 2 than Plan 1 based on our average number of minutes that we talk in a month? Well, we can't tell exactly. This table's great because it's kind of visual and it helps us build on things, but we can't tell exactly. We can see Plan 1 is cheaper at 150 minutes, and then at 200 minutes, Plan 1 is more expensive. Not by very much, though. So it's somewhere between 150 and 200, and I'm going to say it's closer to 200 because this is only a $2 difference, and this is a, what is that, $4.50 difference. So I'm going to say it's definitely between 150 and 200 and probably closer to the 200 end. So the next thing that they want us to do is they want us to write linear equations for these. So again, I'll kind of try to color code these. If we do the first one, so for Plan 1, I'm going to say P1, we're going to start with, can't even remember now, $15.99, and we're going to add that 13 cents per minute. And then Plan 2 is the easy one. It's $39.99. And if you want to, you could put plus 0 times m, but I'm not going to mess with that. So now it says use the equations you found in question 3 to find the number of minutes a customer would have to talk for the plan to cost the same. And I'm going to come back to this, and I'm going to do number 5 first, because I think it's good to see it visual before we do it algebraically. So plan 2 is, I'm going to do, I don't know why I can't remember to do this, with a red line. And I'm going to do that one first because it's easier. It's just the consistent. So for plan 2, at $39.99, it's going to be, essentially right at $40 no matter what. Actually amazed I was able to stay that straight. Okay, so that's for plan 2. Now for plan 1, we're going to start at $15.99, which is, basically for a graph you wouldn't be able to distinguish it from 16, so it's right about there. And then I'm going to pick one of my points off of the graph, or off of the table, so I can use it. So after 300 minutes, it was at $54.99. So 300 minutes was at 54. This is 55, so $54.99 is right here. Okay. And then I'm going to use the handy dandy tool here to connect those. Okay. Okay, so there's our two lines. So the question then is, where do they cross at? Well, it looks like it's awfully close to, what are these going by? 120, 140, 160, looks like they're going by 20s. So it looks like it's very close to 180 minutes where they cross at. So now let's do that algebraically and see what we get. So this looks like it's close to 180 minutes for both to be $39.99. So now let's see if we do it algebraically what we get. And I'm going to do that down here because it's going to take a little space. So, or not down here, I'll go over here. So I want these two to equal, and the trick that we want to do if I want those two to be equal is just write the two equations equal to each other. So we want $15.99 plus 13 cents a minute to be the same as the other plan, which is always $39.99. So I want this equation to equal the other equation. And then I'm just going to solve this. If I subtract $15.99 from both sides, then I get 13.13 M here. And then over here I get 24. And what this represents is there's a $24 difference between the two plans to start with. That's what that 24 represents. So now, if I want to get to the minutes, I'm going to have to divide by 0.13. And I get that the number of minutes that we need in order for these to be equivalent is whatever 24 divided by 0.13. So we have that extra $24. And how many minutes at 13 cents each do I have to talk to make up for or to be equivalent to that extra $24? And it comes out that it is 184.6. So looking at the graph, we were pretty close. We said it looked like it was pretty close to 180. You can see it actually crosses a little bit past 180. So 184.6 is what I'm getting on the calculator if I round it. So they're equivalent at about 184.6 minutes. So now just a little conclusion here. Do our answers in questions 2 through 5 confirm or conflict each other? They confirm each other. I mean, we knew from the table it was, between, not sure if I'm in the right spot here. Yes, I am. So we knew it was between 150 and 200 minutes for sure. then when we looked at the graph, we said it looks like it's close to 180, maybe a bit more. And then when we did the equation, we got that it was 184.6. So even though the other two didn't get exact answers, the table and the graph, they weren't wrong. We just couldn't get the exact number. We knew it was around 180. We knew that it was somewhere between 150 and 200, probably closer to 200. So everything fit together. They all confirmed each other. And then you're just going to have to look back here and decide for yourself how close was your prediction. And then the last couple things, it says here, to make an estimate of your own personal monthly phone use, which of the plans would be better for you? So are you someone who actually talks on the phone a lot anymore? A lot of us don't talk on the phone a lot. We do a lot of texting. So do you think that you would, which deal would be better for you? And again, remember, if you talked more than 184 minutes, then you would have to, you should use the second plan, the $39.99. If you talk less than that, you should use the plan 1 with the charges per minute. And 184.6 minutes, remember that's like 3 hours. 180 minutes would be 3 hours. So that's like 3 hours and 4.6 minutes. Actually, when they charge you, they would probably charge you for 185 minutes because they usually don't split that by parts of minutes. If you go into a minute, then they charge you for the whole thing. And then this one says to pair with at least 2 other students and brainstorm some other types of monetary decisions you could make. And this is the type of thing, I mean, you could use this for cable bills, for phone bills, for anything where you're charging a certain amount per hour, or per hour or per minute, but the starting amount is different. So you could do this with, you have 2 different people that are going to come do work at your house. You have 2 different places that you want to rent. You have 2 different types of bills, just all kinds of things you could do with that. So in 17C, we're going to look at relationships that aren't perfectly linear, but that are close to linear. So it's entitled Close Enough. So we're going to look at data where it goes up in somewhat linear fashion, but the points won't fall all exactly on a line like they did with our past examples. So it says, throughout the 20th century, life expectancies steadily increased. Now, what we mean by life expectancy is this is the birth year after 1900. So 0 means actually 1900. 10 would be 1910, 1920, 1930. 100 would be the year 2000. So if you were born in, this is your birth year, so if you were born in 1900, you had a life expectancy on average of 47.3 years. If you were born in 1910, you were expected to live to be 50. Now, again, remember this means this is when you were born, not when you died. So if you were born in 1910 and you were expected to live 50 years, that means you were expected to live until 1960, just so you kind of understand what we're looking at. If you go up here to, some areas where a lot of people that are taking the course would probably be, in this area, at least probably the 60s or 50s, mostly up in here. Look at these. If you're in 1990, if you were born in 1990, you're expected to live to be 75 and a half. If you were born in 2000, you're expected to live to be 76.8. Now, these aren't perfect. These are just averages. It's not like everybody's going to live to be 75.4 years old. And we don't know if they're going to hold true because we won't know, like these we would know if they were true or not now because this was 1910 and 50 years later it would be 1960. So that time has passed. But these ones up here where we're going into the future, 2000, we won't know if the 76.8 is true until we get past the year 2076, 77. Even then we don't know for sure because there'll still be some people that are alive and we're talking about averages. So, these are things that we don't know these things for sure, but they're an estimate of what they expect to have happen. So, has life expectancy increased at a steady rate since 1900? And the answer is no. And how do we know that? Well, if it increases at a steady rate, then the difference between each of these, since these all go up by 10 years, the difference between each of these should be the same. And if you go from here to here, that went up by 2.7 years. Okay, let me get a little bigger pen here. Okay. If you go from here to here, it went up by 4.1 years. And so on. It's not an equal amount. From here to here is 5.6. So steady rate means it should be going up by the same amount. So how do you know it's not increasing by the same amount each 10-year period? Okay, so for number 2 it asks, which decade appears to have the greatest gains in life expectancy and which appears to have the least? So if we go up here and we can calculate these. From here to here, 59.7 to 62.9 would be 3.2. Hopefully I don't mess any of these up, just doing them in my head. Stop doing them in my head. So 68 or 62.9 to 68.2 would be 5.3. This would be 1.1. This would be 2.9. 75.4 minus 73.7 gets us 1.7 only there. And then this gets us 1.4. Okay, so the one that looks like it had the most was from being born in 1920 versus being born in 1930. So if you were born in 1920, you were only expected to live to be 54.1, but if you were born in 1930, you were expected to live to be 59.7. So the which decade? So that would be 1920 to 1930. The least, so the greatest is this, the least is going to be, was it 1.1? So that would be 1960 to 1970. So the difference between being born in 1960 versus being born in 1970 was not that great of an increase. Now, if you look at some of the bigger increases, you might ask yourself, why did it go up that much? Well, a lot of this has to do with healthcare. It also has to do with whether or not we have a good economy. It has to do with whether or not we've made any, we're in any wars. So there's all kinds of things. 1920 to 1930, this was, a time of a lot of some medical advances. Same thing in this area. You were finding, vaccines for polio and things like that. So, somebody that was born in 1950 would have to be concerned with some of those things that somebody in 1960 would not have had to be concerned about. And then in the 60s, I'm not saying there weren't any medical advances, but there weren't these huge medical advances that would have, added a large amount of life expectancy. So we also didn't have any. We had Vietnam in this era, but that would have not been people born in 1960. That would have been people born in 1950. So you have to it's hard to kind of keep track of it, because when you're talking about the things that happened in, say, the late 60s or the early 70s, you're talking about the people that were born back here. So somebody that was in a war here would have been born here, and that's how things affect. So anyway, I'm going beyond what they're asking anyway, so we'll keep going. So pick any two data points and find the slope of the line containing them. Make sure to include units. So I'm going to do, this is going to be very closely related to this. So if we pick two that are in a row, this number that we found between them will be helpful. So if we picked, say, I'm going to do this over here. So if we pick 1970 to 80, we should get it should have something to do with this 2.9 years. So what does it have? Well, you want to increase, what's the increase in life expectancy per year? Now we know that in 10 years it increased by 2.9. So we're going to do, again, I'm going to do 1970 to 1980. And we know that the increase in life expectancy from 70 to 80 was 2.9 years. And that was, I'm going to put life expectancy because we have years and years here. Years is in the date and then the life expectancy. So 2.9 years life expectancy for 10 years of time. Okay, so now if we divide that, we get 2.9 divided by 10, which just shifts the decimal over, and we get 0.29 years in life expectancy per year. So every later year that you were born, you gained 0.29 years in life expectancy. Now it says any 2 data points, so I don't have to do 2 consecutive. I could do from 70 to 100, or from, let's go back and do some that are back here. So let's say 1910 to 1930. So if I did from 1910 to 1930, do that down here. So 1910 to 1930, that would be an increase of 20 years time. How much did it go up from 1910 to 1930? It went up by 9.7. So 9.7 years of life expectancy gained in 20 years time. So if we divide that, we get roughly 9.7 divided by 20. We get almost it's 0.485. I'll just say exactly. So it's exactly 0.485. So you gained 0.485 is very close to 0.5, which is half. So you gained about a half of a year of life expectancy for every year later that you were born. So somebody born in 1911 versus 1912 would have 11 would have a half a year less life expectancy than somebody in 1912. Now, the 0.485 is to note, if you go back up here, remember if you went from 10 to 20, you got 4.1, 20 to 30, you got 5.6. You notice that this 4.85 that we got is in between that, because it was basically combining those 2 decades together and averaging them together. It says pick another pair of points and find the slope, which we already did. If your 2 slopes are not the same, average them together. So we could go from here and average those together. So 0.485 plus 0.29, and then if we average that, we get 0.3875. So the average between these is 0.3875. One way to do this, if you were going to do this and try to find a slope for a line here, is to go from I like to go from the very first point to the very last point. That's often the most accurate. So you don't have to, there's different ways you can do this. You just have to follow what it asks in the homework and go from there. I won't ask you to find the slope for these ones that aren't exact, so you don't have to worry about that, about seeing that on an exam. Okay, so it says even if a relationship is not perfectly linear, it might be appropriate to model it with a linear equation. So this equation represents what's known as a trend line. It also is called a line of best fit. So sometimes you'll hear that term, line of best fit. So it's this line that we can try to go through the middle of this data as closely as possible. And even though it doesn't hit every point, you can see that it kind of goes along with the points. Every once in a while the point's a little high or a little low, but this line fits through it fairly well. So the trend line for this first graph, this is the data that we just looked at. Notice how the trend line is close to most points. They're about the same number of points above and below, and so on. So now it says, hey, let's play. You go ahead and play this game. Use a straight edge to draw a line that best represents the trend line in each graph below. The line should be close to all of the points with about the same number of points above and below. Now when you're doing this, two different people are not going to get probably the same answer. But our goal is when we go, across this again, we want it to kind of go close. So it looks like if I'm going to do this one, it should kind of go like this, which means to me it looks like it should start a little bit higher here so that we could kind of go under these and down. So I'm going to grab my line segment tool, and I think if we go from about here to about, hold on, I messed that up. So if I go from about here, and you can kind of play around with it a little bit, you'd be using possibly a straight edge if you're doing it by hand. And that looks like that gets about as close as we can to, if I go up here, then I've got a lot of points below. If I go down here, I've got too many points above. So I'm trying to get it so it's about even. And to me, that looks about right about in there. Okay, so that's all they're talking about. And it's not an exact science the way that we're doing it. There is an exact way to find the line of best fit, but it's kind of a long, complicated process. And so it's not that complicated, but it's tedious and long, and so they're not going to have us do that by hand. So now let's do that again for the other one. I'm going to use a different color. Again, I kind of want to eyeball it because I need to know where to start. It looks to me again like maybe we want to start just a little bit high here and then go up about like that, maybe right about in there. And it's not perfect, and you're not always going to go, above here and above here, but that for this one, that looks like it's about as through the points as best as we can. Now, this is the life expectancy for males, so they've separated out this data. This was all people. This is the life expectancy for males only. This is life expectancy for females only based on the year they were born. So it says use the trend line you drew on the male life expectancy graph to estimate a slope and y-intercept. Use them to write an equation of the trend line. So if I go back up here to the male one, what does it look like the starting point is? Because that would be my y-intercept. Well, it looks to me like it starts at about, this is 40, this would be 50 and 60, so it's looks like it's right at about 50. So I'm going to say that y equals 50 as a starting point, and then I want to know how much it goes up. So again, what I usually do is I usually just go from the beginning to the end. So it looks to me like it starts at 0.50 and it ends at, or not ends, but close to the end here, is that 60? It looks like it's almost right exactly at 100 and 100 over and 70 up. And again, I'm not looking at this point, I'm looking at this line. So I'm looking at this point here and this point here, not the actual data points that were there before. So after 100 years, or the year 2000, it looks like the life expectancy is at 70 for males. So what's the slope there? If I went up by 20 years in life expectancy over 100 years in time, then that means I went up by 2 every 10 years, or 0.2 every 1 year. So my slope is 0.2. It looks like we're going up 0.2 years for every gain in a year. So I'm going to call this, these are like my x's and these are my y's. So I started at 50, and it looks like what I'm doing is sloping up at about 20 years per 100 years. If I divide that, I get 0.2. So that's my slope. So now it says to do the same thing and to estimate a slope and y-intercept for the females. So if I look at this, where does it start at? Well, it looks like this point right here at the end of the line is at about 0.52 maybe. So this looks like at about 0.52. And then it looks like it ends at about 100. And then up it looks like it's maybe, this would be 90 and this is 80, so about 82. So 182. And that's for this point right there. And so my equation for this would be y equals, and you can use a different variable there. You could use E equals, expectancy equals, or whatever. I'm just using typical y and x. And I'm saying it starts at 52. That's the y-intercept. And it goes up by 52 to 82 would be 30 years gain in life expectancy over a 100-year time. So if I divide that, just like up here, if I divide that out, 30 divided by 100, I'm going to get 0.3 increase in life expectancy for each 1 year time. So that's my slope here, 0.3x. So it says, write 1 or 2 sentences comparing the slopes of the trend lines for male and female. Also compare how well the lines model the data. Are they fairly close to the line? So I would say these lines model fairly closely. There's no points that are way off the line in either of these graphs. So I'd say they're pretty good trend lines as far as how they fit the data. And then the slopes, if you were going to write that out in a sentence, the slope for the women's is increasing, or is larger, so they're gaining more life expectancy. And again, why do women, if you notice here, we've got 82 for, they started out not that far off, 50 and 52. But the women have gone to 82 while the men have only gone to 70 over that time period. Well, why is that? Well, a lot of things, but I'll just name a few that I've seen studies on off the top of my head. Men are bigger risk takers in general than men. Than women. They'll do things like drive motorcycles fast and cars fast and things like that. They also have a lot of times men. In general, again, it's not saying all the time, but in general, men tend to have more physical jobs, doing things that are more dangerous. So a lot of times it's jobs, you're talking about factory jobs and construction jobs and things like that that aren't as likely for women to do. And so those types of things. Also, there's been lots of studies about the fact that women will seek medical help when they're not feeling well more readily than men will. So all of those types of things add to the fact that women's life expectancy has gone up at a faster rate than men's have. And so even though they used to be fairly similar because they were both doing a lot of physical work, you think about 1900, men and women were both doing a lot of physical work. They both had the same lack of health care, those types of things. But now you've seen it get a wider gap in it. Okay, so now it says the scatter plots below show many different sets of data. Decide which ones you think might be reasonable to model with a linear equation. Well, I don't even like how good these are. I wish these weren't quite so good. But obviously B and D you could model with a linear equation. Well, that's too high. It should have gone through the points. But, these both are going in a somewhat linear motion or linear increase. And it doesn't matter whether it's going upward or downward. It's still linear. If they're falling somewhat in a line, then we say it's a linear relationship. Now, they don't even have to be this good. You'll notice the ones we had over here weren't quite that good. And in fact, these were still pretty darn good. But what is wrong with these two? I would be pretty hard pressed on A to know where I should put a line. Now I'm not saying there's not a pattern, but it's a U pattern, and we want to know which one could you model with a linear equation, with a line. Well, I could model this with some sort of a U or a V, but to put a line in there, which way do I put the line? If I make it go upward, then I miss all of this points. If I make it go downward, then I'm way off from these points. I mean, honestly, the best fit line through this would probably do something like that to try to get as many above and as many below. And that doesn't describe the data well at all. This says the data stayed steady, and it didn't. It went down and then it went up. So this just is not well modeled with a line. Same thing here for C. If I was going to model this with a linear equation, I'd probably have to do something more like that. Probably even a little lower than that. Let me try that one more time. So it'd probably be more even like this to try to get, you know, some points below and some points above. But that doesn't represent this data very well. This data came, you know, went very slow, and then it started to raise quickly. And if this data continues in this trend, this line is just going to get worse and worse as we go. So these two, not saying they don't have a pattern, but they don't have a linear relationship. And so it says, consider the ones we decided would not be good candidates. Write down a description of the characteristics that helped you eliminate it. So I'm just going to conclude with, they do have a pattern, and they may not have a pattern. You may come across a scatter plot that just looks like buckshot, like somebody shot a shotgun at the page. But these do have a pattern, they're just not linear. So that's what I would say. The characteristics are that although the scatter plots do have a pattern, they don't fall in a linear pattern. They don't fall in a line. So now we're going to conclude this this unit by looking at some budget increases, and we're still talking about personal financing. We're still talking about modeling data, and we're going to look at this situation where we have electricity usage. Electricity usage is measured in what they call kilowatt hours. So this kWh means kilowatt hours, and the first question here says, or not first question, but it says the table shows a sample of actual energy usage and a monthly electric bill amounts for a small apartment at various times during the year. How does this data differ from what we had before? Well, some of the things that you might notice, if you look here with the energy use, you notice they don't have this from smallest to largest like we did in the past, and they don't have an equal increments, like we were usually talking about, like 10-year increments or things like that. So these are just random energy uses throughout the year, and they're not in any order or pattern. Also, then that means over here we can't look for, like, did it go up by the same amount every year, because this doesn't go in a pattern. That's not going to help us. So because it's not in any sort of order or pattern, that's different than what we've had. So now it says create a graph of the data points and use a straight edge to draw a line that passes closely. So I'm going to try to get these graphed. Let's see if I can zoom in a little bit. All right, so we have 198, 38, 34. Oh, and in the past I've noticed that this is not labeled very well. I mean, we need to get up to only, well, I guess it's not too bad. We didn't need to get all the way up to 1,000. All right, we'll leave it the way it is. So 198 and 38.34. So 198, this would be 2, 3, 4, 5. So these go by 50s. So this is 50, 100, 150, 200, 250. So if I'm trying to do 198, I want to be close to 200, and then 38.34. So I'm going to be a little bit shy of 200, and then these go by, it looks like tens, or by 1, 2, 3, 4. Okay, so 20, 40, 60, 80, 100. So these go by 20s. So this is like 20, 40, 60, 80, 100. Gotta get a thinner pen since I zoomed in. So we've got 20, 40, 60, 80, 100. This would be 120, etc. Here we've got 50, 100, 150, 200. And it's really important that you notice what the scale is before you start putting these on here. So I've got my 198, 38, which would be right about here. So very close to 200, but not quite, and then not quite to 40. So it's right about there. Put a dot instead of a star. Okay, so right about here. Then my next point is 699, so essentially 700, and then 114.84. So think of that as like 700, 115. So 700 would be here, and 115 would be, this is 110, or 100, this is 120, so 115 would be out here. And then we have 366, 63. 366, 63. So there's 250, 300, 350, 400. So 366 would be about here, and then I need to go up to 63. 66. $33 would be sorry, this one's giving me a hard time here. 366, 63, right about here, I think. So this would be 300, 350, 400. So 366 would be about here, and then 63 would be a little bit above 60. And then the last one, 741, 117. So 741 would be a little bit before 750, and then we want to go up to 117. So up to 117 would be almost 120. So right about here. So these are, again, far from perfect because the scale is so, the scale's so big. We had to go all the way from, a low of 198 up to a high of 740, and from a low of $38 to 117. So that kind of stretches this out a little bit. Now it says to use a straight edge to draw a line that passes closely to all the points. So we're going to do like we did before. For me, I'm going to grab this tool. If you were doing it at home, you might just use a ruler or something. But it looks to me like I want to put a line somewhere right about there. It looks like this point's a little low, this point's a little low, these ones are a little higher. So it looks like I want to go right along there. Let me try that again. Use a thinner line, and let me use a different color so I can see it. Okay, I don't like that. That looks like it's too high, so I'm going to try again. I'm still too high. I need to angle that down a little bit. So as you can see, this is not a perfect science. So let me try going a little lower here. The way that we're doing it's not a perfect science anyway. It still seems like it needs to be angled down a little bit more. So maybe more like this. There we go. That looks a little better. So that one looks like it hits the data points fairly well. I'm even going to go just a tiny bit lower, I think. There we go. I like that better. So that goes through the points, I think, fairly decently. So now it says, use the line you drew in question 2 to make an estimate of the electric bill in a month when the consumer used 500. So we're going to go back to our graph, and we're going to say, well, what if they used 500? What do we think their bill would be? Well, here's 500, and we're going to go up to the red line and see what we think it would be. So 500 is right about there. If we follow that over, it looks like it's a little bit more than $80. So it doesn't look like it's $90, but above 80. So maybe about $82. We're just estimating. Somebody else might draw their line just a little bit differently and get a little bit different answer, but that seems reasonable for what we have. Okay, so now it says use the data to determine an equation for the line. So we're supposed to take the 198 and 366 and determine an equation for the line. And I'm going to scratch this because I do not agree with this. You're really not supposed to use the original data points to determine your equation. You're supposed to use points on your line. So instead of doing what they're saying to do, I'm going to go and look at the beginning and the end of my line here, and I'll use here since that one isn't. And I'm going to use that. So if I'm doing that, what is my y-intercept? Well, it looked like my y-intercept, I'm going to back this up so it's not all covered up. It looked like my y-intercept was just below $10, maybe $9. So it looks like it starts at about 0.9. And so we have a first point of 0.9. And then if we come over here and we try to get one that's here towards the end, this would be 800, 123, 124, something like that. So 800, 124. And so if we're going to write an equation, the first thing we need to know is the y-intercept. Well, we know that's 9. It starts at 9. And then how much does it go up? Well, when we went from 0 kilowatt hours to 800 kilowatt hours, so how much, we want to know how much money it's increasing per kilowatt hour. Well, the money went from $9 to $124. So what's the difference between those? So 124 minus 9 gets us 115. So we got a $115 increase for an 800 kilowatt hour increase. So if I divide those, my slope comes out to be 115 divided by 800, and it comes out to be about 0.14. So it's like 144. So we're losing, or we're gaining about 14 cents or 14.5 cents, a little bit more, every kilowatt hour. So I'm going to put 0.144 per kilowatt hour. And I'm going to go back actually and change the y to a c for cost. So the cost is, it appears from the graph, about $9 to start with, and then it looks like it goes up a little bit over 14 cents per kilowatt hour. Why is there $9 initially? Well, most services, there's an initial fee, whether it be your phone or your electricity or your cable bill. You can add on things, but there's usually like a starting base number. So now it says use the equation we found to estimate when it's 500. So we're going to see how close. Remember up here we estimated at 82. So let's look at our equation now and see how close we are. So our equation was y equals 9 plus 0.144 k. So if we do 500 kilowatt hours, that would be y equals 9 plus 0.144 times 500. And hopefully we'll get something fairly close to that. So 9 plus 0.144 times 500 is $81. So we actually did quite well. Comes out to be exactly $81. So write down a sentence describing the advantages. I'm not going to write a sentence, but you know, what are the advantages? Well, this one right here is quick. This one is probably a little bit more accurate. So the good thing about looking at a graph is it's quick. You can just pick the point off the graph. The good thing about an equation is it's usually more accurate, more precise. So to the nearest cent, how much cost is added to the bill for every kilowatt hour? So we said about 14 cents. 0.144, that's in dollars, so if I put that in cents, it's like 14.4 cents. It says the tenant of the apartment decides to install a dishwasher. The model she chooses will use about 15 kilowatt hours per month. How much is she going to add? Well, if she's adding 15 kilowatt hours, and a kilowatt hour is 14 cents, I'm going to use the 0.144. It's not going to be very much. It's about $2.16. So it's only going to cost her about $2.16 to use that dishwasher. And then the tenant knows from past years that her electrical usage spikes in August. due to the need for air conditioning for Texas summers, and she estimates that her usage in August will be approximately 1,000 kilowatt hours. Using the equation we created, estimate how much she should budget. So this is what they mean by the equation that we created. We created this equation right here, and we're going to use that to figure out what it would be for 1,000 kilowatt hours. It's going to be, it's going to be close to double this, but since this has a starting amount, it's going to be just a little bit more than, or a little bit less than double. So 144 times 1,000, 9 plus 0.144 times 1,000. She should expect to spend right about $153. This is not perfect, but at least she would know, hey, I've got a budget around $150, $160. And so it would give her a good idea or a good estimate of where she's going to be at. So that concludes Unit 17. And on the final, there will be material off of Unit 17 and 18. The best place, besides getting your homework done, the best place to study is the review, because the problems on the review are what you're going to see that are similar to the test. So I will try to finish up with Unit 18 and get that up shortly, but that is the end or the conclusion for Unit 17.